Let's now move from theory to practice. SCIANTIX is an open source code available on GitHub. In the training branch, you can find tutorials, input files, and executable code. SCIANTIX simulations are defined from 4 input files: history, settings, initial conditions, scaling factors. Based on these files, you can use SCIANTIX to simulate both constant and transient irradiation conditions. Now we focus on the stationary intragranular behavior of fission gases. SCIANTIX models how xenon and krypton atoms produced by fission reactions diffuse inside the grain and become trapped in intragranular bubbles. It also describes the resolution process, where bubbles dissolve, releasing gas atoms back into the lattice. This competing mechanism controls the retention of fission gases inside the grains and their availability for migration towards the grain boundaries. The intragranular behavior strongly influences the overall swelling of the fuel and the onset of fission gas release. Let's start with a simple stationary case. We simulate a fuel grain irradiated at constant temperature of 1373 Kelvin, with a constant fission rate density of 10 to the 19 fission per cube meter second and no hydrostatic stress. The total irradiation time is set to 5500 hours. This setup allows us to observe the basic mechanism of gas production, diffusion, trapping, and release under stationary conditions. The input initial conditions file defines the starting conditions of the simulation. It specifies fundamental properties such as the initial grain radius, the initial gas concentration. By setting these parameters, we describe the physical state of the fuel grain at the beginning of the simulation. After defining the initial physical state of the fuel, the next step is to configure the simulation settings. The settings define which physical models are activated for each phenomenon. For example, whether intragranular diffusion is considered, how grain boundary saturation is modeled, how trapping and resolution processes are treated. The settings allow you to select different modeling options to adapt the simulation to specific conditions or experimental setups. In this tutorial, we use the default settings, which correspond to validated models for standard UO2 fuel behavior. Let's look at the results. The xenon produced increases linearly over time as expected. A portion of the produced gas remains trapped inside the grains, either in solution or in intragranular bubbles. Another fraction reaches the grain boundaries and accumulates. Once the grain boundaries saturate, fission gas release begins. Another important result of the simulation is the evolution of the intragranular bubble concentration. At the beginning of the irradiation, many small bubbles nucleate inside the grains, leading to a sharp increase in the bubble concentration. After that, the bubble concentration decreases with time because of the resolution process. This phenomenon is a key feature of the microstructural evolution of nuclear fuel under irradiation and impacts both swelling and fission gas release. Lastly, as irradiation progresses, the bubble radius increases due to the trapping of additional gas atoms.